Hello, I'm going to talk today about some of the practical challenges of scaling up AI on computers. In particular, I'm going to dwell a little bit on what that means for memory systems. And at the end, I'm going to introduce you to Graphcore's chip and system for tackling this problem. So, we are all trying to discover how to do intelligence mechanically, how to harness artificial intelligence in computing. Over the last few years, of course, it's no secret to anyone here, there have been major breakthroughs, in particular in the area of generalization. This is what deep learning is all about. It's about not so much memorizing all of the data that a computer has experienced, but generalizing from the general properties of that data to do useful things. For example, absorb a large body of text and then automatically write newspaper articles. I'm going to talk mostly about deep learning today, so mostly about generalization. That's not all of AI. AI also has to learn how to attend to the right data. It has to learn when to produce output. And it has to distinguish between memorizing interesting or important facts and generalizing about the background of data that it has experienced. But today we'll talk about generalization because that is the heart of deep learning, which is where all of the compute action is currently at. So our problem in AI is a scale problem. In order for AI to be truly useful, we have to be able to make it more powerful than a human. Humans are actually quite cheap to produce, and quite cheap to employ, and quite cheap to educate. So we could easily produce more humans. But the real objective here is to produce superhuman AI, AI that can do things that we can't. Think of what it would take for you to trust a machine to act as your doctor. It would have to be better than a trained human doctor, or to give you advice about which stocks to invest in. You'd have to trust it to be better than a human. Otherwise, you'd go to a human. Likewise, autonomous driving. The challenge is not so much controlling the vehicle or recognizing where the pedestrians are. It's working out what the other humans who are driving vehicles are going to do. In other words, our AI has to be at least as smart as humans at understanding other humans. That probably requires that it's got the same sort of intellectual capacity or knowledge capacity as a human. And a human happens to have about a couple of 100 trillion synapses of about half a byte each, as far as we can tell. So say 100 terabytes of learned information in your brain. This is a very sweeping generalization, of course, but it must be of that order as far as we understand today. So we're probably, if we're going to harness things that are at least human level knowledge capacity and intellect, we probably need to explore models of that sort of size, 100 terabyte models, much, much bigger than we have explored so far today. If we just scale where we are today, it will be very, very expensive. So after we've worked out how to do 100 terabyte models, we then need to work out how to make them efficient, economically efficient. Let me give you some baselines just so we know the numbers we're talking about. So some recent and fabulous work by the team at OpenAI have managed to, at least for what we know today, about unsupervised learning, which is a particularly important class of learning for AIs. They've managed to work out the relationship between the size of the model, the amount of compute required for that model to learn from a body of data, and the amount of data needed for that model to reach its potential. And the relationships are roughly as I've shown here. The data scales roughly as parameters to the 0.4, and because compute is the product of parameters and data, that scales roughly to the 1.4 in the parameters. So if you go up 10x in the scale of the model from today, you need roughly 2.5 times as much data, and you're going to do roughly 25 times as much compute in flops sense. GPT-3 today, one of the largest language models so far produced, and truly amazing in its capability, and yet still far short of a human, has about 175 billion parameters. So it's maybe 1,000 times smaller than a human brain. We shouldn't be surprised that it's not quite human comparable yet, but it's still amazing. It was trained on 300 gigabytes of data, or 300 giga-word pieces, strictly speaking, so roughly that sort of order. And it required about 300 zettaflops to train it. Now, a zettaflop, thousandth of a yottaflop. A yottaflop today is about $1 million. That's what it costs you, roughly, to do a yottaflop in a piece of cloud infrastructure or an owned data center today. If we scale this sort of model directly up to 200 trillion parameters, which is roughly brain scale, then we'll need about 6,000 yottaflops, about $6 billion to do that training once. Today we don't actually know how to do that in a stable way, but when we learn, it'll clearly be too expensive. So the efficiency challenge is writ large. Now, machine learning evolution so far has taken place in a couple of phases. I say so far, really since about the breakout point of deep learning in the early, roughly 2012, AlexNet, for example. The first phase was all about perception. It was all about learning the relationship between two different representations of the same data. For example, given a set of pixels in an image, work out whether it's got my girlfriend, mother, cat in it. That's roughly what your cortex does in your brain. It's not all of your brain, but it's clearly a very important part. And the challenge with this first phase of the breakout of useful AI was that the data was very expensive. There was much talk about how expensive the data was and how limiting that was to the future of AI. And the reason it was expensive is because that type of learning was supervised. In other words, the data needed to be curated. If you want your AI to understand or to recognize your cat, you have to give it lots of example pictures of your cat. So someone has to prepare pictures of your cat, and you have to prepare pictures of other cats that aren't yours and other things that aren't cats. And if you did that, it would learn the difference. So supervised learning, which is at the heart of perception or learning to do a specific task. Now, the second phase of the breakout of AI happened a couple of years ago, maybe 3 years ago, and is associated with structures called transformers, things like BERT and GPT. And this was all about overcoming the data problem by allowing the machines to learn on their own. In other words, unsupervised or autonomous learning. This makes the data cheap, especially if, for example, a good source of data is language. You can simply absorb the internet into your AI. In fact, humans have spent about 6,000 years writing down what they know, so there's a lot of human knowledge captured in language. And if we build a machine that can absorb that without supervision, then potentially it can learn a lot, much more cheaply. And this worked marvelously with this structure called transformers. The only downside of that was an explosion in the size of the models and the amount of compute, the cost of compute to train them. So there is a third phase, hotly anticipated. It is a work in progress. And this phase I'll characterize as being all about sparsity. Really, it's about how do you take these very high-capacity, super large models that have been learned autonomously and make them economically efficient. And really, that's a question of taking a big model that's learned without any supervision and then adapting it cheaply to make a small model in a supervised way to do a specific task, sometimes called distillation. So those are the three phases of AI so far. There may be others. And the third one is a work in play, like I say. The large model issue, of course, is definitely with us. Just to recap on the first reason why, it's because we want superhuman capability. The second reason why is to do with the unsupervised learning. If you don't know what the eventual objective of learning is, because you're learning in an unsupervised way, then you have to learn everything about the data. If I give you a book and ask you to read the book, and then at the end I'm going to ask you a question, if you don't know the question in advance, you have to remember a lot about the book. If you do know the question in advance, you don't. It's as simple as that. So we will definitely need to expensively train large master models of things like human language and what's in images and stuff like that. and then distill them down to task-specific models that are much more efficient and much cheaper to operate. There's another reason why large models may well be efficient. In fact, there are several, but I highlight this one. And that is that learning slows down as you reach near the capacity of the model. And it may well be that actually it's more efficient to partially train a very big model than to get close to saturating the capacity of a smaller one. Right, let's look at the master algorithm of learning as we know it today. This is SGD, stochastic gradient descent. Three very easy sequential parts to the algorithm. First of all, forward propagation of activations towards a cost function based on mappings, layer-wise mappings defined by a set of weights. And then once you reach your cost function, you compute a gradient of the loss against your activations, and you propagate that backwards through the network. This is back propagation, to compute gradients of the loss with respect to activations, again using the weights. So that's the first step. The second step then takes the activations on the forward path and the gradients with respect to the activations on the backward path, and works out from that the gradient of the loss with respect to the weights. In other words, how to adjust the weights to reduce the loss. So those two processes occur simultaneously and for a long time. And then once you have accumulated some information about how to adjust the weights, the gradient of the weights, GW, then you can update the weights. And that's one iteration of SGD. And typically today, to learn a large model, you might do that 100,000 times on many, many billions of samples of data. I admit, I omit from this all of the stuff that actually makes it work. Now, the problem with SGD, the reason why I'm labouring this point, this won't be news to you at all, is that outside of the operators, which are actually highly parallelizable because they're big matrix operations, but outside of the operators, there is no parallelism exposed by this algorithm. It is sequentially dependent forward and then backward on all of its terms. So how are we going to take an algorithm like this and speed it up by building a big computer, short of just speeding up the operators? Of course, we've spent some time trying to speed up the operators, and we're quite good at it. In fact, we have inherited much knowledge from HPC over the years about how to do linear algebra effectively, and we built definitely better chips to do that with low precision AI numbers. But we'd like to go beyond that. We'd like to not only speed up the matrix multipliers, but speed up the whole algorithm. Well, there is one thing that helps, and that is SGD operates on batches of data. And you can extract parallelism from the fact that the data comes in batches. How do you do that? Well, there are various ways, but there are a couple of ways which I'm going to highlight. The first one is simply to use multiple copies of your model and give each copy part of the data. So multiple replicas, each copy gets part of the data. This is called data parallel training. It is ubiquitously practiced. It's very easy. The different learners, I've shown 4 here, all start to learn slightly different things because they've got different data. So periodically you synchronize their weights, you average them out. Then they all learn the same model. But actually you can do slightly more with batch data. You can also build pipelines. Now you wouldn't think in an algorithm that requires that you walk forward down a set of operators and then walk backwards again, that pipelining would offer anything, but actually it does. And again, the reason why it does is because you can actually divide up the data that goes down the pipeline into sub-batches, micro-batches, I've called them, and you can stream them down the pipeline. And although there's a dependency for each of those micro-batches, that means that you have to go all the way down the pipe and all the way back up before you can complete your compute. They can all overlap with each other in the pipeline. I'll show you a picture shortly. So I'm going to choose an example. This example is actually going to turn slowly into BERT, which is a well-known language model, implemented in this way on 16 processors. I'm going to use 4 copies of the model. Each copy is a ring of 4 processors, and I'm implementing a pipeline on each of those rings. The pipeline is actually not 4 stages long because I'm going to walk along the line from 0 to 3, processor 0 to processor 3. Then I'm going to loop back to processor 0. And the reason why I'm going to do that is this is a language model, and that's where I put my shared embeddings. The embeddings occur at the front and at the back of the model, and I want the same data to be used for both. Having gone through the forward path of SGD in that way, I then go backwards along that path. So I go from 0 to 3 to 0, and then from 3 back to 0. So the actual pipeline depth is 9 in this example, even though there are only 4 processors in each ring. So here's a picture that shows how micro-batches allow you to overlap work and achieve parallelism in this sort of setup. I've shown each of those brightly coloured lines is one of the 4 processors. And if you home in on one particular colour, such as orange, you can see a micro-batch walking down the pipeline from 0 to 3, going back to 0, then going back to 3, and then back up the pipeline to 0 again. It does that in a way that's spread out over time, such that it can be interleaved with other micro-batches. So once the pipeline is full, you have actually achieved full 4-way parallelism here. And what's allowed you to do that is the fact that you can split the batch of data that you've got into small pieces. Now, the downside of this is it draws from the same pool of parallelism as replicas. And replicas are generally easier to deploy. So in other words, if I can have a batch of a certain maximum size, and that's usually limited by the algorithm, why would I use pipelining when actually it'd be easier to split into many replicas? You're probably not going to have a replica right down to the level of 1 sample of data per machine, because then the machine won't be efficient. You probably need a few samples of data in each machine. But say you have a global batch size of 10,000, perhaps you give 10 data samples to each machine and you use 1,000 machines. Why would I use a pipeline instead? Well, the answer is I can deploy more machines if I also add pipelining on top. And the reason for that is it allows me to spread the flops that I need to do on each of those data samples across more chips. So short pipelines, so long as you've got a reasonable batch size, turn out to be very efficient. You can probably see that even with just a few samples passed through this pipeline, it does fill up quite quickly, and even the fill and the drain at the end don't take much time, much of the elapsed compute. So long as you can reasonably balance the work being done in each stage of the pipeline, you can get close to 100% efficient with short pipelines of 2 or 4 or 8 processors typically. There is an alternative to pipelining which draws on the same form of parallelism, and that is that you can walk a processor down the pipeline. In other words, rather than a processor in the pipeline staying in the same place and using the weights relevant to certain layers in the pipeline and passing activations and gradients that it's computed to its neighbors, what we can do instead is we can move the processor with those activations and gradients. In other words, they stay on the chip, and we upload new weights. So it's as if the processor is walking down the pipeline. This is generally easier to load balance than a pipeline, a literal pipeline. But it does require more loading. It requires more memory traffic, because loading of the weights actually is an additional load on the memory. Nevertheless, it's quite attractive for large models because the compute intensity of large models is higher. In other words, for a fixed number of flops, the amount of weight loading goes down. So that's an alternative and is well known and widely practiced. We can also exploit various forms of parallelism within a stage laterally. So we could take one stage of our pipeline and split it across 2 or 4 processors. This is particularly easy to do in things like the point convolution operators, which are very common in neural networks, for example, pervasive in transformers, because they are embarrassingly parallel in that dimension. The problem with trying to split sideways across chips is that not all layers are friendly to that. So there are often transpose operations that flip between micro-batch style parallelism and lateral tensor split parallelism. Again, it works well for a small number of processors in that dimension, 2 or 4. Beyond that, the transpose operation and the total number of flops usually turns out to be a limit. And there's one last trick which is very, very useful before I go into some actual numbers which which will converge on a key point. And that is recomputation. So because when I walk back up the pipeline of SGD, I need to reuse values that I have computed as I went forward down the pipeline, that implies I have to memorize a lot of data. Now, in practice, I don't have to memorize everything. I can memorize periodic snapshots. And when I come back up the pipeline, I can recompute locally the forward values from those snapshots. This is what I've shown on the right. The box marked A stashes the input activations to a set of 4 layers in this case, and allows me to recompute the values A when I come back up the pipeline, and I've marked those recomputed values RA on this example. So that, again, very widely used and very powerful paradigm. Right, let's put some real numbers on it so we can quantify exactly how this stuff all adds up. So this is BERT BERT large implemented on exactly that structure of parallel pipelines, each pipeline with 4 processors in it, pipelines 9 deep. I've taken the example of phase 1 learning of BERT, where the sequence length, the number of tokens or the number of data quanta, which is where the Q comes from, is 128. The number of features in the model is 1,024. I'll leave you to look at these numbers offline, but the key points are, if I can accommodate state on a processor of about 330 megabytes in this case, for resident weights for some layers of BERT, in this case 7 layers of BERT on this processor, and also if I can do a certain number of flops, in this case I've assumed maybe the processor can do 100 teraflops. I can buy machines that advertise 300 teraflops today, but in anger, 100 teraflops is a good number for a processor chip for this sort of application. So if those two things are true, in other words, I have enough memory on the chip to store 300 megabytes and I can do 100 teraflops per second on the chip, then the amount of input-output bandwidth I need, both to my neighboring processors and to the memory that's off the chip, is really very modest. It is just below 300 megabytes per second. Not gigabytes, not terabytes, but megabytes per second. And that's really interesting because you do see very large numbers advertised for memory systems of AI chips, bandwidth, and you also see obviously a constant bandwidth chase in the chip-to-chip interconnect of the AI chips. But this shows a very real case, where actually the numbers are really modest. But it does hinge on being able to store a reasonable amount of information on the chip and also achieve a reasonable number of flops on the chip. There are some further notes to this example, some alternatives, which I'll leave you to read offline. So the key point here is concerning the off-chip memory. If we have of order a gigabyte of SRAM on our chip, which is effectively a perfect memory, 0 latency, infinite bandwidth, then it turns out there's no obvious case for high bandwidth off-chip memory, which is interesting because almost all solutions in the market today have high bandwidth off-chip DRAM. The priority for DRAM should be capacity for the off-chip DRAM, because we need those human scale models. And we don't want to only be able to operate human scale models on computers that are the size of a warehouse. We'd like everyone who can afford a chassis or a rack of machinery to be able to at least manipulate a pre-trained human scale model and distill smaller models from it, even if that person can't afford ever to train the thing from scratch. So that model has to live somewhere. It will live on off-chip memory. It can't live on chip. It's too big. And it turns out that the only suitable form of memory we have for doing that is actually server-class DDR, not HBM. So we don't need the bandwidth of HBM, but also HBM has 2 other issues. It's very, very expensive, partly as a result of the assembly yield, but mostly as a result of margin stacking. In other words, someone who sells you HBM has to buy it, first of all, from the manufacturer of the memory and integrate it into their processor product, and then they sell it to you with their margin on top. Now, that doesn't happen with server-class DDR because you buy it from the memory manufacturer directly. It only has one margin. The net effect of that is that today, HBM is about 5 times the price of server-class DDR per gigabyte. The other issue is that HBM has no roadmap beyond about 72 gigabytes per chip today. So to build a 100 terabyte memory system, or many 100 terabyte memory system for a human scale model implies that you have to purchase thousands of chips with a few tens of gigabytes attached to each. And therefore only people who can own a warehouse scale computer could ever do that. You couldn't fit it in a rack scale computer. There is, of course, underlying both DDR, server class DDR and HBM, the same memory technology. But the differences in form factor mean that one has high bandwidth and the other one has high capacity. And in the AI space, the AI accelerator space recently, everyone has been chasing bandwidth. And I think that's misinformed. I think it should be chasing capacity. We don't actually need the bandwidth. So, just a reminder, there are therefore three user scales for people who might want to buy and own or rent an AI computer. There'll be a very small number of people who will train enormous, terascale models from scratch on enormous bodies of data and may be able to afford to spend a yottaflop doing so, or 1,000 yottaflops doing so. But there won't be many of those. What they'll train is universal models of things like human language, all human languages together, or universal models of medical knowledge or legal knowledge. And from those universal models, other companies will just rent those and distill from them task-specific models to do valuable things. So they will need to be able to take a model of that size, but not actually have enough flops to train it from scratch, but just use many fewer flops to retrain it to do something specific. And retraining does take many, many fewer flops than training from scratch. And then there's a third class of users of AI machines who will do neither of those. They will just take the smaller, say 10 billion parameter, task-specific model and deploy it in their business to do useful things. So in the last 5 minutes or so of the talk, I'd like to just introduce you to Graphcore's technology. It's a chip. It's software that runs on a chip, tools that run on a chip that present common user interfaces, and also a system, a chassis, that we sell as a computer itself. It's designed from scratch to do AI, and it's informed by some of the thinking that I have just laid out. It's informed by a lot else besides, but this is only a half-hour talk. So our view strongly is that the purpose of a computer is not only to execute known algorithms efficiently, but also to enable and support the discovery of new algorithms. And that statement couldn't be more apposite than in AI today. We are really at the nascency of understanding how to mechanize AI. And the sorts of models we're using have changed dramatically over the last few years. They'll probably change dramatically over the next few years. The final solution may not be neural networks, or it may be neural networks with this third phase of goodness, which is the sparsity phase built in. They may look very different. They may make different demands on a computer. So a good computer at this stage of the evolution of AI is one that is flexible enough to allow the discovery of new algorithms, as well as efficient enough to run today's algorithms well. And of course, it's probably obvious, or at least it's my belief, my strong belief, that AI algorithms are very unlikely to run optimally on platforms that were originally designed for and optimized for different workloads, such as graphics. It may be a serendipity, but I don't really believe in serendipities in our field. I think it's much more likely that new architectures designed from scratch for AI, which is a very, very unusual compute workload, will ultimately win out. However, they'll only win out if they emerge quite quickly, because algorithms and software development tools, everything else, it all bends towards machines that exist. And it may be that as a world of humans, we miss out on the best machines because we're too slow to inject new thinking into this market. So Graphcore's mission is to not be slow and to inject quickly. Here is a very simple software abstraction which underpins our technology. So we assume that the job to be done is represented by a graph, hence the name Graphcore. The graph has two types of nodes. So tensor nodes that hold data. They can be anything from a scalar, a vector, or any number of dimensions you like. And compute nodes that we call vertices. Obviously, they're both vertices, really, but we call the compute nodes vertices. The compute nodes can be stateful. In other words, each time they're run, they can remember state from last time they were run. The edges that connect these things can form loops. They don't have any state in. So this is a pretty unconstrained compute graph of data holding objects and compute holding objects. The reason why we differentiate the two is because data usually needs to be spread across multiple processors, whereas compute can usually be broken into tasks that only need one processor. So it's important from the point of view of mapping it to a parallel machine. And a final key point on this abstraction is that all the communication that goes on, in other words, all the traffic over the edges, is foreseen at compile time. Now, that doesn't mean it necessarily occurs, and obviously the compiler doesn't know what the data to be carried will be. But the compiler is always aware that some data may, at a certain time in the running of a program, need to move from one node to another node. This allows us to schedule optimally, i.e. at compile time, communication. And the reason for that is in a massively parallel computing world, communication is part of the program. It's as much as a part of the program as floating point arithmetic. And just as we wouldn't blink before compiling the arithmetic, likewise, in a massively parallel machine, we need to compile the communication to make it efficient. So here's a floor plan of our chip. It's really only got three parts. Or three components on it. It's got some very, very big numbers. We have set the record for the second time, the largest chip ever built at 59 billion transistors. It's actually built in TSMC's 7 nanometer process and is 823 square millimeters in size. It's the same size as everyone else's chips. We're all limited by the reticle size of the fabs. It has 1,472 independent processors capable of running their own independent programs, and they send messages to each other. So these processors implement those vertices. The processors also have local memory attached to them, 624 kilobytes per processor, which gives us nearly 900 megabytes in total on the chip, so of order a gigabyte, as I mentioned earlier. There's a massive communication fabric that allows all the processors to talk to each other at any time without blocking. And because all the traffic over that fabric, which we call the exchange, is compiled, it means there are no queues. You don't even need addresses, in fact, because that exchange fabric is actually completely synchronous and deterministic. So a tile will simply send information onto the exchange fabric, not knowing where the information is going. It doesn't need to know. The compiler knew. So the compiler just knew it needed to send at a certain time. And someone else, a few clock cycles later, will know that it needs to receive, and it'll grab that piece of data as it flies past. So the exchange fabric is an almost perfect electrical interconnect because it burns no power on queues or contention or addressing even. It only burns power for data that actually moves. And then the third component we've got on there, apart from lots of these compute tiles of memory and the exchange fabric, is some links that allow us to connect chips together. We also have a couple of links that connect us to a host CPU or something like that, which is where we get data from. But the main feature of these links is that they allow you to build to build large arrays of these chips in such a way that a cluster of these chips looks like a bigger chip. In other words, the software abstraction remains the same. Now, this is just an interesting trace from our tools that show exactly that BERT example I showed you earlier running on 4 IPUs. There you can probably make out 4 stripes, one for each IPU, and the colors show you that the machine alternates between phases of doing compute on the tiles locally, and then phases of exchanging information between tiles. So the compute is pink, the exchange is blue, and from time to time, in order to for the program obviously to remain in step, the tiles need to synchronize with each other, and if a tile has finished its work, and another tile has to wait on a result from another tile, then obviously some time is lost to synchronization. And you can see here in yellow the time lost to synchronization. So number of clock cycles along horizontal axis here, and each of the 1,472 tiles and what it's doing is in the vertical axis. And you can probably use your built-in optical estimator, your eyeballs, to work out that in BERT there we're probably spending, I don't know, 60% of our time doing compute, probably 40% doing exchange, in other words, communication, and the rest is lost to waiting or synchronization. And that's a fairly typical result. The tile processors, the 1,472 of them, are each dual path long instruction word processors. They have a main path, which is a control path that operates on integers, spends most of its time working out addresses and control counters. And then a fatter floating point path that we call the auxiliary path, which is where all the heavy lifting arithmetic is done. It actually executes on a pipeline which is 6 slots deep. And in order to make the operation of vertex code as deterministic to the compiler as possible, so the compiler can do the best job of scheduling efficiently this highly parallel machine, we actually have an unusual threading system, which it's a form of barrel threading, in which there are actually 6 slots in the barrel and 7 thread contexts. And the reason why there are 7 thread contexts is because there's a supervisor thread whose job it is to dispatch vertex work to each of possibly 6 worker threads. When the machine boots up, actually there are supervisor owns each of the 6 slots in the pipeline, but the supervisor can launch a worker and in so doing delegates that slot for as long as the worker requires it in the pipeline, and the worker context cuts in and uses just that slot in the pipeline. So the supervisor can see the pipeline, and the workers crucially can't, because they're interleaved with each other. So the workers look like they're operating at 1/6 of the speed on a machine that has no pipeline. This makes them really easy to schedule deterministically in the compiler. Anyway, there's some detail you can look at offline there. Everyone's always interested in peak arithmetic, so the peak arithmetic of this machine is achieved for 16-bit IEEE floating point numbers when we're doing blocks of 16 by 16, whether it's a matrix multiplier or a convolution. And we have the unusual property that we can stream one of the dimensions of those matrix multipliers from memory. So rather than the 16 by 16 by 16, it's a 16 by 16 by n block of compute. When we're doing 32-bit multiplies, actually the block size is 4 by 4 by n. So we have, as well as 250 teraflops of float 16 matmul performance, we have 1/4 of that for float 32, which I think is the highest performance of any float 32 chip available today. And the mixed precision stuff, when we're doing 16-bit floating point arithmetic, most of the intermediate accumulations are actually held at high precision. It's only every 16 terms that you have the option to round down to 16 bits to save memory. And then obviously, when you recover from memory, you can recover back up to 32 bits. And finally, I'll just show you a platform that we've built that delivers this technology. We call it the M2000 IPU machine. It has 4 of our Colossus Mark II chips in it, in a ring. It exposes some more IPU links through sockets at the front that form a second dimension of ring. And in fact, on the right-hand side, you can see that you end up with a 2 by n torus. And what's in the box is the pink piece there, a 2 by 2 slice of that torus. The torus is asymmetric because that suits the workloads. And the vertical height of the torus depends on how many of these machines you bolt together. I've shown a rack there with 16 of these machines plus 4 servers. We call that an IPU pod. The machines have a built-in host, but it's a very, very lightweight host. It's a proprietary chip we call a gateway, and that just acts as a host for data feed and for boot to the IPUs, and also supports bulk DDR in the form of 2 DIMMs, 256 gigabytes capacity altogether, possibly more in future, but today 256 gigabytes. And also a NIC, a 100 gigabit NIC, to connect this device to a network. So this is very much a disaggregated chassis for building out large compute infrastructures. and the chassis just contains the IPU compute piece, and you can combine it with servers and storage and other network components to build powerful computers. The programming interfaces we present today are TensorFlow and PyTorch and Onyx, and also all of the other stuff that sits above those, like JAX, for example. And that's it from me today. IPU is intended as a machine that is performant for today's workloads. And in fact, if you go to our website, you'll see some very good examples of us performing well on today's workloads. But equally importantly, it's a general purpose processor with what we believe to be the right characteristics to enable algorithm discovery in the AI space. Thank you.